Find the equation of all tangent lines to y equals 9 minus x squared and through the point 112. What I want to do with this problem is kind of take a look at the general concepts of this unit as well as this specific problem. So I'm going to first take a look at the graph. We have 9 minus x squared. So this will be at 9. We'll have 12, something up here. There's going to be two different tangent lines that we can see. There's going to be one in this vicinity and one something like this. And since this curve will go down faster, it'll only hit at one point somewhere in that vicinity. So now, what do we need to do? We're going to have to first figure out if I have some point here on the curve. Let's call it a comma f of a. Now we're going to have to talk about tangent lines from this. So if it's going to be tangent, we can find the slope of the tangent line to the curve at this point a f of a. We can also find the slope using these 2 points. Once we've done that, we can set them equal. So let's first start by finding the slope of the tangent at any point a comma f of a. So what are our 2 points? Going slowly through it, it'd be a comma f of a, and I'll just write what is f of a over here. That'd be 9 minus a squared. And then our point, we'll have a general point on this curve, which is x comma f of x. Now let's first start by finding the secant slope. Remember, secant is the slope between 2 points. It's also known as the average rate of change. So we'll have y2 minus y1 over x2 minus x1. In other words, change in y over change in x. This right now is our secant slope. What do I have to do to my secant slope to make it the tangent slope? So you can think of it, here's a point x comma f of x. I want this point to go to a. If x goes to a, then all those secant lines are going to be approaching one line, the tangent line here. So I want the limit as x goes to a. Now at this point, you just need to simplify this. The 9's are gone. We have a negative x squared minus a squared. So how about a negative of x squared minus a squared? Give me a couple minutes. Over x minus a. The limit as x goes to a. Now we can factor that out at the top. We have x minus a times x plus a over x minus a, and the limit as x goes to a. Remember, we're going to need to write the limit every single time. We can reduce this out, and we can now find this limit, and we get negative 2a. So what this is saying is the slope of the tan line equals negative 2a. Now I can also find the slope using the points 1 comma 12 and a comma 9 minus a squared. So we'll have 9 minus a squared minus 12 divided by a minus 1, which simplifies to negative 3 minus a squared, or let's say negative a squared minus 3 over a minus 1. So now what can I say about those two things? They are still representing the same line. So we have negative 2a equals negative a squared minus 3 over a minus 1. And now we just need to solve that, multiply both sides by a minus 1. We'll get negative 2a squared plus 2a equals negative a squared minus 3. Move everything to one side, we'll get a squared minus 2a minus 3 equals 0. Move that up a little. A minus 3 times a plus 1. So a equals 3 or negative 1. Now what do we need to do? We need to find the equation of the tangent lines. So if a is 3, we're going to plug it into our equation, and we have y equals 9 minus x squared, so 9 minus 9 would be 0. And then if a is negative 1, then 9 minus 1 would be 8. We know that the slope is going to be negative 2a, so we have a slope at 3 will be negative 6, and our slope at negative 1 will be positive 2. We can just plug in, we have y minus 0 equals negative 6 times x minus 3, and we can write just y equals negative 6 times x minus 3, and on the other one, y minus 8 equals 2 times x plus 1. And let's check over here on this one that's intersecting somewhere on this side. That would be the equivalent to 3 that has a negative slope. This agrees. And we have a negative 1, 8 that has a positive slope. That agrees. And that looks good. So we need to know the difference between our secant, our average rate of change, and our tangent, which is our instantaneous rate of change. And what this thing has given us is our instantaneous rate of change for any a value. And we'll expand more on that as time goes.